A car's diffuser is arguably the most important aerodynamic part of the car. The other contender would be the underbody, but given that the diffuser is part of the underbody, it kind of makes sense that it is the most important part of the car, aerodynamically speaking. A good diffuser can reduce a car's drag while increasing its downforce. That not only helps the car go faster, but also accelerate faster and turn faster too. And as such, diffusers have really improved a lot in the last 40 years. They used to be pretty much nothing, like literally just a flat plate and a continuation of the car's underbody. Then they became something similar to what we see today, where they're angled up a little bit to kick that flow up and increase the downforce and reduce the wake size. If you want to see a good early example of a good diffuser, then on our YouTube channel, we did a video a couple weeks ago called Mercedes Evo 2 Aerodynamics. That featured a CFD simulation of the Mercedes Evo 2, which was designed back in the 1980s, and it looks quite similar in the general aspect of the diffuser that we have these days, and it was very cutting edge back then. But even though diffusers were starting to emerge in the form we're familiar with now, the underneath was still exposed, where you had all manner of things from the exhaust to the fuel tank to the piping, etc., all just exposed. So the flow would hit it and potentially separate, thereby reducing the diffuser's effectiveness. Then the next major improvement in the diffusers was covering this region, so now that it was flat underneath. That improved the quality of the flow over the diffuser, but that wasn't enough, and thankfully even more diffuser innovations have taken place since that, and diffuser guide vanes are becoming more and more popular. And in our video we published just this Saturday past, called Rimac Navero's Groundbreaking Aerodynamics, that car has these guide vanes, and we go through how they improve their diffuser's performance. That is now a short history of diffuser design up until now. But for those who love wings like myself, a natural idea is to use wings underneath the diffuser to help kick the flow up. It might seem a little weird, but let me explain the potential reasons why it might be a good idea. So in figure 13, if we zoom in, let's get a general idea here. So let's zoom in. You can kind of see these wings underneath the diffuser, and they have a few potential benefits. The first is that you now have another surface to direct the flow up more. So you're not just relying on the actual diffuser itself, but now these additional wings. And wings are very good at doing this exact same thing. The second reason why wings could be good here is that wings naturally produce lift or downforce depending on how they're oriented. So it really seems like a good idea there too. Then finally, having these wings here potentially squishes the flow onto the diffuser. So the flow has to race through this opening between the wings and the diffuser. That means that it is less likely to separate over the diffuser. That means you can operate it at a higher angle of attack, and that means the diffuser works better. So given all these potential major benefits, it warrants at least looking into this idea of putting wings underneath the car to help direct the flow up. And that's what we're looking at today. We're seeing if putting these wings underneath helps the car's performance and the diffuser's performance or not. And to do that, we're looking at this paper called, if I scroll up here, Ground Effect of an Inverted Double Element Wing Diffuser on a Sedan Car. It's open access, so you can find the link below, and the DOI is at the end of this page here, just around here. And I'm really excited to see the results of this study because I think this idea holds a lot of promise, and I think that more cars, you could use more wings really everywhere, and this is the start of it. So in figure 1, if we scroll down here, we see the car the researchers used to investigate this idea. It's a really ugly car. It has all the modern features though of a regular car, so while it isn't going to win any beauty pageants, it still works. And one thing that I'm actually not sure about is that they say that it's a Nissan Sunny car. It doesn't look exactly like a Nissan Sunny. I don't know, maybe it's the projection view that they have, or they squish them to fit into a page. I don't know, it looks weird to me. But anyway, this has all the general features of a regular car. The underbody, the A-pillars, C-pillars are quite nicely rounded. The back of it, all these things are pretty much how you'd find them on the regular cars. So the aerodynamics from this is fairly representative of a regular sedan. Now in figure 2, we see the wings that they're putting underneath this car, and it should be noted that this is a 2-element design. That in its own right is an important point because 2 wings operate together. They can exhibit very different behavior to just when 1 wing is isolated. So for example, the gap between the 2 wings, so just around here, introduces faster moving flow over the second airfoil, and that allows it to be more aggressive than the first one and not stall, as you can see here. we have that happening where the first wing is installed at an angle of attack of 4 degrees, the second wing is at 15.5 degrees. And the main reason why you'd want to use a multi-element design is that it's easier to get flow attachment over several wings with these gaps in between than having a much larger wing and that is curved much more in an effort to try to get the same amount of downforce. In other words, you can get more downforce out of a multi-element wing than just using a one-element wing. And that is what these researchers have done here. Another thing to notice is that each wing has a different airfoil cross-section. So you can see this shape here for the first wing is different to the second wing. The larger one, this first wing, is a Clark Y airfoil, which is like one of the earliest airfoils ever designed back in 1922. And it's a good one. It still hangs around today. That's how cool it is. So some details about it is it has an 11.7% thickness to chord ratio, and that maximum occurs at 30% from the leading edge. And that right there gives us a really strong indicator how this airfoil is really very similar to the much more popular NACA 4-digit series, particularly the 12% thickness airfoils. So the NACA 4-digit series also has the maximum thickness at 30% from the leading edge too. It also has quite a bit of camber, 3.4%, which occurs at 42% from the leading edge. That's just a touch further back than the 4-digit NACA series, where the maximum camber occurs at 40% from the leading edge. One of the major benefits of the Clark Y airfoil is that it stalls at fairly high angles of attack, around 15 degrees. And the start of the stalling phase is quite gentle too, so there's some warning, and that's partly because it is a fairly thick airfoil. But anyway, the second smaller airfoil is an LS10413. This is a little well less known, but it's slightly thicker at 12.9%, and that occurs much further back at 37.5% from the leading edge. The maximum camber is 2.4%, and that occurs really far back at 65% from the leading edge, so past halfway. Now looking at the tail of this airfoil, it's quite supercritical. What that means is that the tail is pinched, and that increases the Mach number you can fly to without getting shockwaves and the massive increase in drag. That's called the critical Mach number, and if you want to learn more about that, check out another video on our YouTube channel called Aero Fundamentals number 31, critical Mach number. But here, the critical Mach number isn't important because this wing will get nowhere near that. But there might be another reason why the authors selected this airfoil here, and that's because supercritical airfoils often have higher stall angles of attack because the nose is more rounded than the 4-digit and 5-digit NACA series airfoils, for example. So you can see here it's quite rounded, a bit more than the Clark Y2. So with the Clark Y compared to that, this other airfoil with a fully turbulent boundary layer can go to about 5 degrees higher without getting stall. So this second wing is actually really designed to handle a much worse flow than this first airfoil. And the fact that this second airfoil is placed behind this first airfoil, which means it's going to be seeing more turbulent flow as well, indicates that the researchers did some really good thinking here and selected this airfoil on purpose to really handle this worse flow coming from this upstream wing. Now, these wings have an aspect ratio of 2.89%, which isn't very much, and normally that would then produce a lot of induced drag. But in figure 3, if we scroll down here we go, we can see that there are end plates on the wings, and that will really cut down the induced drag, which is really good. So for the overall simulation, the free stream velocity is 30 meters per second, which is 108 kilometers per hour, and that gives a Reynolds number of 13 million for the entire car. Now, the height off the ground and the distance from the rear will likely affect the wing's diffuser's design performance. So how far this wing is off the ground and how far back and forwards. To address that, the researchers tested all these configurations in table 2. Let's zoom in a little bit here. Here we go. So the height of the wings from the ground ranged from 119 millimeters to 154 millimeters. And the authors have done a good job converting that into a non-dimensional number of the height of the over the wing chord, which we can see in this third column here. So these values range from 25% to 33% of the wing chord. What that means is that this bottom wing here will be anywhere from 25% of the wing's chord from the ground to 33%. They also changed the length gap between the first and second elements called delta 0 here, which we can see in figure 4. So if we can kind of see here, let's zoom in a bit on this second figure here. Okay, so delta 0 here, we can see in this part, and that is the height distance between the end of the first airfoil and the start of the second airfoil. They also changed this, sorry, that was the length distance. The height distance is delta G, which is the height distance between them as opposed to length distance. So just make sure to keep that in mind. So they changed those two distances between the two airfoils to see how that gap size will affect the airfoil's performance. And then also normalize that to the chord. So we have delta 0 on C and delta G on Z, which is a nice touch. So that's the general geometry that they tested. Let's now move on to their simulation setup. So in figure 5, we see their domain, and they have a good sized one. Now, they don't say how they simulated the wheel rotation, at least from what I can see in the paper, but at the end, near the references, they have a list of nomenclature for the paper, and they mentioned MRF, which stands for Moving Reference Frame. This term doesn't appear anywhere else in the paper, but I'm pretty sure that they use the MRFs for the wheels. So that's a pretty decent approach. For the simulations, they use Fluent, which is a great CFD software, but a bit expensive. On the other hand, you could do all of this with OpenFOAM, which is a completely free and very powerful CFD software. And if you want to learn OpenFOAM, then check out our courses here. Now, the authors have done a pretty good job on their mesh. For example, their Y+ values are around 1. Their mesh quality seems good. They say that they give some metrics. They say that the aspect ratio is always less than 5, which is a good rule of thumb to follow because, and even more so if you have a very swirling flow, you want to get the aspect ratio down so that the length in each direction is approximately the same. Now, they also do a mesh independent study where they change the cells from 2 million up to 32 million, and that's an impressive range to test. We have the results in figure 7 here, and they show the drag coefficient on the y-axis and how much that changes. And we can see that across these number of cells, it doesn't change that much. Now, it should be noted that this is a RANS simulation though, and the effects of time on the flow are kind of ignored. And I say kind of because the time effects do still bleed through between iterations, but not nearly as much as if you were to incorporate the time element. But it doesn't matter that much here because they also only simulated half the car. That's to reduce the number of cells they needed to solve here. Anyway, they show that the drag coefficient from 12 million cells up changes by only 2%, so they went with the 12 million cell number. That would then make it approximately 24 million cells if both halves of the car were simulated. Now, in figure 8, we see them testing out 4 different turbulence models to see which one performed better. The K-epsilon, the K-omega, the SST K-omega, and the realizable K-epsilon. Here they all performed pretty similar, but the only one that is really different is the K-omega, and that's pretty bad. Like, there's quite a bit of wobble in here. The other 3 are definitely much more similar and much more stable. So in practice, the automotive industry has kind of moved on from the K-epsilon family and is now very much with the SST K-omega model, which is a good one, is much better. But here the researchers decided to go with the realizable K-epsilon model because it was quicker and gives good results for this particular setup, which remember is half a car with RANS. So if you're watching this and you're going to do car simulations at some point in the future, go to the SST K-omega turbulence model and save yourself some trouble. Now, to validate their CFD, they compared the drag coefficient of this regular car without the wings with the drag coefficient published on the Nissan Sunny website. They say that the values are within 1%. Now, I don't know if that's right because, as I said, the car looks pretty weird. It doesn't look exactly like how it should, I guess. But anyway, instead, they tested this car as well in a wind tunnel and scaled that down to 1/18th of the regular size. They also put pressure tappings along the car to see where the pressure coefficients were rising and reducing. And in figure 9, we see the results here, as well as a comparison with their CFD. Here we go. So this is the pressure tappings, the pressure coefficients along the car. And they both look pretty good. So the experiments are the dashed red line, and the CFD results is the solid black line here. And they're not accurate enough to give a 1% accuracy in the drag coefficient, but they're pretty good still. They get all the major effects down. So overall, I don't think that this accuracy is 1% in the drag coefficient or the lift coefficient, but I think more around 10% or so would be a better number to follow. So let's keep that in mind and move on to the results. So in figure 10, we see some pretty interesting results. So the graphs are a little tricky to understand, so I'll explain them first. Let's zoom into the first one here. So the top one here is how the lift coefficient changes with the ride height, which is the x-axis. But note that the car isn't changing its height itself. Instead, the wings are getting further or closer to the ground, and the car height is remaining the same. So in effect, the wings are just moving up and down. But in addition to that, the different colored points here also represent different gaps between the wings. So 10 millimeters means that the main wing was 10 millimeters lower at the trailing edge than the second wing was at the lowest point on the airfoil, as shown in figure 2 here. If we scroll back up here, 10 millimeters is this height here. This gap is 10 millimeters. So really the take-home message is here, how much higher one wing is than the other for this first plot. So first, the blue line shows that the change in the lift coefficient isn't monotonic with the different ride heights for the wings. It wiggles around. Now, I'm not sure how much of that wiggle is within the Aero though. If you kind of smooth it over, that wiggle here, it will kind of show that the wings have less of an effect on the lift coefficient as they get further away from the ground. Now, one thing to note is that the y-axis, if it's a positive value, that means that it's a reduction in the lift coefficient with the wing system compared to without it. So I know that these graphs are a little confusing to see, but anyway, what that means is that generally speaking, as the wings get closer to the ground, less lift is produced and even more downforce as a general trend. As for how the distance between the two wings affects these results, so these colored lines, these colored plots here, these dots, as that gap gets larger, the wings have less of an effect on the lift coefficient. And I think the reason is that the further away the wings are from each other, the less they act like a multi-element system. And they just then act like two wings separated and they're kind of isolated from each other. So the conclusion from this graph is that to get as much downforce as you can out of the diffuser, you need to put the wings closer to the ground and keep them closer together so they are a multi-element system. Now for the second graph, we really have the same conclusions because the different color plots correspond to different lengths the wings are away from each other. And the closer they are, the more they affect the lift coefficient. And I think the reason is the same here as before because the closer they are, the more they act like a multi-element wing and not just two random wings not really interacting with each other. So that's the take-home message for these graphs. Put the wings closer together and closer to the ground to get the most downforce. Now in figure 11, we see the same graphs, but now for the drag coefficient. And note that a positive value on the y-axis corresponds to a reduction in the drag coefficient. Here, the further they are from the ground, these wings, the greater the drag reduction. So I guess that makes sense because the further away from the ground they are, the closer to the car they are. And so that will then kick the flow up more into the car's wake, I guess. We'll see later on if that's the case. As for the height distance between the two wings, so these colored dots here, that shows that the drag coefficient is kind of insensitive to how close they are. I mean, even at 40 millimeters, there's only a 4 count difference, which is definitely within the error of this simulation. And likewise for the second graph, we see similar differences for the lengthwise distance between the two wings. And these differences are just too small. So we can't conclude here that putting the wings closer or further apart will affect the drag very much. So those were the forces. What about the flow fields? Well, in figure 13, if we scroll down here, we see the total pressure plots for the wing system and at different heights off the ground. And going from the top downwards means that the wings get closer to the car and further away from the ground. And I think maybe we can see why, as the wings get closer to the car and further away from the ground, they don't affect the lift as much. So in the bottom plot here, the wings are in the car's wake now. So you can see that the weight coming over the diffuser is kind of hitting the wings as well. So they don't have much fresh flow to work with. And even while for the top plot, some of that is still going on, the wings are more in the fresh flow now, and there is now more energy for them to work with. As such, they will work better. Then the reason why putting the wings closer to the car reduces the drag is maybe because the wings now don't create as much of a wake. That kind of makes sense, I guess, and goes hand in hand with the lift coefficient explanation. So I think at least that's one of the reasons why we see these trends, and maybe there are other reasons too. Now in figure 15, figure 14 doesn't show too much. Figure 15, we see the static pressure coefficients along the underbody. If you scroll down here we go. The static pressure coefficients along the underbody with the wings at different heights off the ground. So it's not until the diffuser section, let's zoom in a bit here actually. So it's not until the diffuser section, this region here, that really any changes to the pressure coefficient occurs. What that tells us is that the wing height isn't really changing how much the flow underneath the car is being sucked through. Now at the diffuser, we then see that the further the wings are away from the car, the more negative this pressure coefficient becomes. That agrees very well with the trend that the lift coefficient is reducing, the more the wings move downwards too. So that's all good, that all agrees very nicely. And that also tells us that as far as the underbody is concerned, the reduced lift coefficient is all just a function of the diffuser region. Now in figure 17, if we scroll down there, we see some streamlines for the car with the wings, and so that's the bottom figure, and the wake is more horizontal with the wings than without the wings. And so that means that with the wings, the flow is getting kicked up a little bit more, and that's an indication that we are getting good downforce now compared to without the wings for this top plot. And that is also the case in figure 18, where we see that there are these velocity vectors, and with the wings, they're kind of pointing up more, and at least the flow is a lot faster in this region. So all these trends really agree with each other, and they're strong indicators that the lift is reducing with the wing system. So that brings us to this podcast. The preliminary results show how wings can improve a diffuser's performance, and I think that it deserves much more research to really fine-tune this design. And it'll be really interesting to see how other designs and how similar effects they are to other wings, and whether the performance can greatly change between the different wings that you choose and how far they are spaced. And if you have multi-element wings like 3 or 4 or 5 wings. So this was all done with CFD, and if you want to learn OpenFOAM, which is a completely free and powerful CFD software, then take our courses below. And if you like this podcast, hit the me likey and subscribe buttons. And if you're staying on YouTube, YouTube thinks you will like this video, so check it out, and we'll see you soon. Peace, amigos.